have discussed the underlying principles about the working stress design. We even immerse ourselves in the different types of crack stages and the corresponding insights about the singly and doubly reinforced. Now we're going to get uh, dwelled on the consideration of the beam flexure theory and the ACI equations, and we are going to top the idea about shear reinforcement. Pleasant afternoon, evening, everyone. Magandang um, merienda at saka early hapunan sa inyong lahat. Let us have this articulation number one. We are asked to determine the moment capacity of the given laid out parameters using beam flexure theory. The AS prime is 15, AS is 50, 6.5 for D prime, D is 25, D for 40, and then the strands of materials here are given as 20.7 and 124.5 respectively. We are asked to find out the moment capacity using the beam flexor theory. And then we are going to utilize the model section, transform section, and this particular stress diagram. This is merely a generic representation of the doubly reinforced. These are not the actual numbers of the reinforcing bars, but in essence, this will be the AS prime, AS, the compression, and tension bars respectively. And we need to convert it into equivalent concrete area so that we can employ the beam flexor theory. This, in essence, is the stress diagram of the compression bars, and this is for the concrete. This will be for the steel. The AT, which is equal to AS multiplied by N as the modular ratio. And this is FT, Fs over F. Let's do it now. We begin the axis. In computing the location of the neutral axis, we are going to equate the statical moment of area for both sides, the upper portion and the lower portion of the assumed neutral axis. And the statical moment of area for the upper part will be the area of the concrete and the equivalent concrete of the compression steel. This will be equated to the statical moment of area of the equivalent concrete of the tension steel. And these are all given except for the X. You will be prompted with an equation, a quadratic in sense, that can be solvable by quadratic formula or any other iterative process or methodology. But in essence, we can solve this one. And this is equal to this value. After computing for the X, we compute for the moment of inertia. For the moment of inertia, we need to consider instead of considering the transfer moment of inertia, as I have covered previously, we are going to utilize the formula for the moment of inertia with respect to the base. And then we compute as well for the moment of inertia of the compression bar and for the moment of inertia of the tension bars. So the distinctions there, other than the representation of the equivalent transform section, will be the corresponding moment arms. So this will be for the concrete, dx cube over 3. This will be for the compression steel. And this will be for the tension steel. And this is the magnitude of the moment of inertia at the neutral axis for the crack section under the beam flexure theory. Then we consider the moment capacity. We start with the moment capacity of the concrete with the formula FCINA over C, that is MC over I for the bending stress. So this FC here is the 45% of the FC prime. This is the computed moment of inertia with respect to the neutral axis. This C is the computed X here. And with that, we can solve for the moment capacity for concrete. and this is equal to
Bakit may bandaan man tinidaanan?
133.34 kilonewton meter. Then we
May traffic
considered
ba ako?
computing the magnitude of
Wala ako.
ms
Babalik ako sa inyo.
with the same relation for beam flexure theory, but this will be Fs over n for Ft, and this is still the INA. This
Ano ka?
E is d minus x. We did compute for the x here. The n is the modular ratio. If we are dealing with the same property of the material, then the modular ratio is equal to 9. So this implies that our moment capacity for steel is 207.35 kilonewton meter. Moment capacity there is this magnitude. Then we have this articulation number 2. Determine the moment capacity of the given layout parameters. By this time, we are going to use the same parameters, but the process is distinct. We are going to utilize the ACI equations. We will follow the same consideration for the representation of the neutral axis, but by this time, instead of x, we are going to represent it as other or numerous papers presented is or notated is it as KD. So we begin with the model section, transform section, stress diagram. So in general presentation of the model section, instead of presenting it as this one, you present it as 1, and that will be AS prime. This bar as 1, that will be AS. In considering the ACI equation, we will be guided by this principle that the governing setup for the compression and compression steel bars and the tension bars, and also for the governing setup for the concrete compression for concrete and the part of the steel that will be considered as the AS1 and this one as AS2 respectively. Well, this will be KD, that's the center of gravity of this triangle here. This will be D prime from the extreme compression of concrete fiber to the center of gravity of the compression bar. And this will be AS2, that will be J2D, J1D. This is the initial moment or couple. This will be the second couple to be considered here. So first, we locate for the neutral axis. We did compute that already, but we can compute this utilizing ACI equation. And with that, we can say that this will be, we did derive the formula for KD. Please revisit our previous discussion here. But KD should depict the same magnitude for X, which is equal to 204.6 millimeters. Then we consider the forces. We start with the compression side. This will be the total C, which is C1 plus C2. This is the area multiplied by the width B, 1/2 FC KD times B. And the AS C2 here, or the C prime, is equal to the product of AS prime and FS double prime. Later on, we are going to compute for FS double prime. But first, we need to derive the formula for the actual compressive stress of the compression bars, which is equal to, by virtue of similar triangle here, we can employ this, and this will be the working relation for it. And this is equal to, please be mindful that this is given. KD has been computed as this one. And FC is 45% or 0.45 of FC prime. FCS prime is equal to 6.36 megapascal. This actual stress of the compression transformed equivalent concrete of the compression bars have to be tested accordingly by utilizing the product of two, the modular ratio, and the FCS prime, which is equal to 114.48 megapascal. Since our allowable Fs is 124.5 megapascal, which is greater than this one, we are going to utilize Fs double prime as this one, the product of 2n minus 1 and FCS prime, which is equal to 108.48 0.12 megapascal. If this one is greater than this one, then what we are going to utilize for Fs double prime is the difference of
Playover. Dire-diretso lang talaga.
Fs and FCS prime. Then with those given and computed parameters, we can have total C or C sub T or C uppercase C, which is equal to 400.4 kilonewtons. Then we consider the tension side, the first part that will be yielded accordingly, and the second part, which considers as T1 and T2 respectively. These are AS1 Fs and AS2 Fs. Then we simply sum it up. Please bear with this presentation. It should be equated to this one. And this is equal to ASFS for the total T. And this T can be computed based on the given allowable and given AS here. And this is equal to 622.5 kilonewtons. Then we compute for the moment capacity with the same consideration of this insights based on this depicted diagram here. We can say that on the compression side, we have the MC as C1 J1D plus C2 or C prime, that C2 as previously presented, C prime J2D, wherein this J1D is the effective depth minus 1/3 of the computed KD. The J2D is the difference of the effective depth and the D prime multiplied by C prime. Then we can compute this one, which is equal to 133.37 kilonewton meter. We do the tension side. For the tension side, we can represent it as M sub T, T1 J1D plus T2 J2D, which is SS, just like in compression side. This can be represented as C sub T or uppercase C multiplied by JD. So in relation to that, we can also represent this as TJD. And this T1 J1D and T2 J2D can be represented this one. In order to simplify our calculation, we know that this MC is equal to CTJD with the aid of this magnitude and the computed C sub T a while ago. We can then have the value of JD. This is equal to 0.333 meter. And this JD can be utilized. We also have the computed magnitude for T. We can then have the M sub T, which is equal to 207.35 kilonewton meter. Well, you know then what is the moment capacity that will govern. So apparently this one. And this has been verified based on the beam flexure theory. Fellow learners, beam flexure theory and the ACI equations of the doubly reinforced rectangular beam. Let us consider the shear reinforcement. So if you were one of my fellow learners before, I often ask you to draw the shear and moment diagram aside from illustrating the elastic or deflected diagram, so that you will know the essence of the correct magnitude for the support reaction, presentation of the shear diagram, the point of zero shear, presentation of the moment diagram, the point of concavity, point of inflection or the change of concavity. Those are vital. For the moment diagram, the moments can be utilized as the value as the design for the main reinforcing parts, while the shear magnitude will be utilized for the design of the stirrups. These stirrups used or intended for the purpose of resisting the internal effect of seismic or lateral forces, which in essence transmitted as diagonal stresses that can be captured or arrested by these stirrups. So let's consider first what we have discussed previously, the design of beams reinforced for tension. We compute for the beam constants. We use the service moment, and then we set up the moment coefficient resistance R
Kasi
with
ibang bus
PD
yung
squared for the service moment as the capacity or the moment capacity. And then we are prompted with two unknowns here. We are actually designing the dimensions of the beam. You can either represent this as a function of D or this one as a function of B by having the guidance of the ideal ratio 1/2 to 2/3 of D and B. Then after that, we compute for the tensile requirement or tensile reinforcement set as AS, which is equal to M over FSJD. This will be further computed by the idea of considering the balance still ratio, rho sub B, and then BD by virtue of the allowable concrete compressive strength that will be FCK over 2FS BD. Then we consider the design of beams reinforced for tension and compression. By the way, this is singly reinforced. This is good for reinforced for tension. This reinforced for both tension and compression is good for doubly reinforced rectangular beam. We consider the C1J1D and we set up this product as MC1 as the balance moment. And then we consider the MC2, which is set in the compression side, C2J2D or AS prime FS double prime J2D. Then we obtain the AS prime, that's the ratio of the excess moment, that's the difference of the service and the balance moment computed, divided by FS double prime J2D. Well, there is a condition for FS double prime. I believe you know this already at this point. Then we compute for MT1, AS1, FS, J1D as balance moment. And then this MT2 and AS2 can be computed based on that with the excess moment divided by FS, J2D. And the AS1 as the balance moment divided by FS, J1D. We take the sum, that will be the tension steel reinforcement. And this is the compression steel reinforcement.
Ano kaya talaga?
Then we consider the shear failure of reinforced concrete. It is more properly called as diagonal tension failure and occurs when there is inadequate reinforcement, known as stirrups, anilyo sa Tagalog, counteracting the inclined stresses. Shear stresses is equal to V, notated as lowercase v, equal to VQ over ID. This V here is the shear computed in our shear diagram. This Q here is statical moment of area. This I here is the moment of inertia. This B here is the width wherein it touches the neutral axis. And if you're going to derive the formula based on this setup parameters, you will arrive at a particular formula. But before I tell you the particular formula, this shear stress act in any section in addition to the bending stress that we did consider in beam flexure theory, My over I. Where are the locations of critical combinations of shear and moment? If you are dealing with large shear and large moment, or small shear, large shear and small moment, this will be the setup taken from what you learned in strength of deformable bodies. But if you are dealing with large shear and large moment somewhere here, this will be the representation of the moment diagram. This will be the shear diagram. Well, obviously, this will have the same comparable magnitude of V because we have the support reactions right here. So this will have large shear at extremities. This will be small or exactly equal to 0. Then we consider small shear, large moment, large shear, small moment respectively within midspan and extremities. For uniformly distributed loading, this will be the moment diagram. And this will be the shear diagram. Take note that at extremities or at supports, the shear is maximum. We also have the continuous beam in the indication of the small shear, large moment, large shear, large moment, and among others. This will be the setup for the shear and the diagram for the moment. The diagonal tension cracks implies the following. If you are dealing with this type of crack, we are actually seeing web shear crack about 90 degrees. This will be flexural crack. About 45 degrees, this will be shear crack. If you if in case you see this type of crack in structural element, so this will be about flexure shear crack because of about 90 degree here and a 45 degree crack here for that sense. This is flexural crack.
Ha? Eh, wala namang alam kasi.
The web reinforcement, known as vertical stirrups, this can be placed in a smaller distance within the supports or extremities of that proximity in similar manner with this one similar manner. In similar manner, we can consider the same comparable proximity of the stirrups here in distances o sa Filipino masinsin dito. In fact, nilalagyan pa nga dito sa may bandang poste. Nilalagyan pa ng anilyo para in order to adhere to the or conform to the recommendation of our National Structural Code of the Philippines. These are the types of the stirrups. And this is a representation of front bars, bent up longitudinal bars. Well, you can cut it right here and extend it about here with a consideration of governing distance from the clear span, from the face of the support, I should say, face of the support. Similar manner right here. If you opted not to set it this way, in longitudinal or bent up situation, so, and this will be extended somewhere here. Extended somewhere here with the corresponding length of embedment and bend length and the corresponding length from the face of the support. You can go back to our previous discussion for the beam detail for that matter. And then the location of critical section for shear design, it's always the distance from the face of the support, the distance from the face of the support. For the portion of the beam requiring web reinforcement, stirrups, so we have, for example, as generic, we have this one uniformly distributed. So this will fall 0 at the middle, so somewhere here will be V. The shear stress, this will be V prime, this will be X, this will be L over 2. By similar triangle, we have V prime is to X, V is to L over 2. The exact shearing stress is the difference of this actual and the allowable shearing stress. That's the V prime. L is the span of the beam. X is the length of beam from support where stirrups are required. And according to code, we need to extend it the distance from both extremities. So, naturally, we consider the area of the column wherein we still provide additional stirrups because of this code policy or recommendation, I should say. The minimum area for the shear reinforcement or stirrups is 0.0015 S. That's the considered transverse dimension, and the spacing of the stirrups here, from here to this one or this one. And a minimum area is equal to pi over 410 squared because the minimum diameter recommended by the code is 10 millimeter diameter. The reason we have 2 here, because on both sides there will be 2 resisting shear action. That's the reason we have 2 as constant here. So 2 pi over 4 10 squared as the minimum AB. Okay. So this will be the articulation number 3. If the strengths of materials are given, design the simply supported beam is carrying 20 kilonewton meter over its entire 6 meter span. Even without dwelling on the diagram of the beam, we are dealing with simply supported beam and carrying a particular uniformly distributed over an entire span. So if you recall your learning discernment in your structural analysis, the maximum moment for that situation is WL squared over 8. And this can be computed as a magnitude 90 times 10 to the 6 Newton millimeter. And then this will be the service moment that we are going to deal with to design the dimension of the beam first before we dwell on the shear reinforcement. As a modular ratio, this will be 9. That is ES over EC. Well, you know that ES is this one, 200,000 megapascal. That's the modulus of elasticity of the steel and concrete respectively. 4,700 lambda. We do not have any given lambda here. And we do not have any specified type of weighted concrete. So if that will be lighted concrete, lighter concrete, so this will be 0.75. Since there is no given here, this will be 1. And this is the square root of the FC. NFC over NFC plus FS can be derived based on the stress diagram, and this is equal to 0.378. J is 1 minus K over 3, which is equal to 0.874. The moment coefficient resistance is equal to 1/2 FCKJ. This FC is 0.45 of the FC prime. This is equal to this magnitude in megapascal or newtons per square millimeters. Then we have the moment capacity as the service moment. We equate that to the product of the moment, coefficient resistance, the transverse dimension, and the square of the effective depth. And we come up with the magnitude using the ideal ratio. So in this case, I utilize D equals 2B. So this will be the representation. So obviously, I can solve for B here. I pre-computed this one, then kindly check for the computation. So this is equal to 244.53, say 250 millimeters. So since this is B, twice of it will be the effective depth. And we add the D prime, which is set as 65. So you can utilize 60 if you want to, but in my case, I utilize 65 for the purpose of instruction. Well, 65 comprises of the concrete cover, the diameter of the stirrups. The concrete cover is 40 millimeters. The diameter of stirrups is about 10. The half of the diameter of main bar, if you utilize 20, that's about 10. That's about 60. Or if you utilize 25, that's about 12.5. That's about 62.5. So in this presentation, I utilize. So then we compute for the dead load, additional dead load for the weight of the beam, which is 0.25 multiplied by 0.565 multiplied by the unit weight of concrete, which is equal to this one, or you can utilize 24. I opted to consider 23.56. And this will be added to the service induced loading in the simply supported beam here, which is equal to this magnitude, 23,328. And then we validate the service load. This service load, we will begin computing for the moment as the service moment. We include already the dead load there. So this will be the moment as we compute this one. Then we compute for the supplied effective depth. We check whether the supplied effective depth will be sufficient enough to hold this type of surface moment. So in this case, with the computed moment and this is constant, the moment resistance coefficient, and the B depends on the magnitude of the computed ratio here or value here. it happened here, the return is 523 millimeters, which is obviously greater than 500 millimeter. We are going to revisit dimensions requirements. So meaning, we are going to again input another magnitude for our algorithm in Excel so that we can have this type of value that will be less than to the effective depth in consideration. So upon providing another value for B, say I did use, I tried to compute this one, obviously. I did consider, well, you can check this one with your you can verify it later with another value, but for the purpose of uniformity and illustration here, I utilize instead of 250, which is obviously greater than, that will lead to a greater value to 500, I utilize 260. So if this is 260, this will be 520, and then you add the 65 here to obtain the age, and then you can compute the dead load with the new dimensions, then the new service loads, and then the new moment, and then new computation of effective debt to be compared not with 500 anymore, but with the new effective debt, which is 520, twice of the considered. And with that magnitude of D computed, 515.09, less than 520, we will accept these dimensions. That B is equal to 260 millimeters and D is equal to 520 millimeters.
Oh, di ba sa ano na to?
Then we start computing for the
Akit ako yun,
tension steel reinforcement or requirement here. So I utilize and pre-computed this one using 28 millimeter diameter reinforcing bars. So it requires 3 of that. So we check now for the shear reinforcement. For the shear analysis, we have to compute the actual shear wherein it will be located the distance from the support. So this will be, so usually we consider it at the center of the
Tingin mo, saan ako pupunta?
considered magnitude, but in essence, in principle, that is about the distance from the base of the support. So this will be, you know this already, this is the support reaction. This 23583.48 is the new computation of the new dimensions as we revisit the requirements for the supply D. And this is the, as I mentioned, this is the new uniformly distributed loading multiplied by D distance, 0.52. You will arrive with this magnitude for the shear for that location. We compute for the shear stress. And as I have told you uttered a while ago, that using the uppercase V as the shear, Q as a statical moment of area, and I as moment of inertia, and B as dimension, you can derive the formula for rectangular section. This is equal to uppercase V as shear, and the B and the D here, the dimension, transverse dimension, and the effective depth. And this is equal to 0.43 megapascal. By the way, you can revisit the strength of deformable bodies. And the allowable is 0.09 square root of FC5, which is less than the actual shear stress. So it requires stirrups. So sumobra siya. No? So itong allowable ay maliit. Dapat mas malaki yung allowable. So kailangan ng stirrups. So we need to compute first the area of the stirrups, which is twice. I did mention about the essence of 2 here. That this will be the coefficient that signifies the reacting situation for the tension drops. This is the area of the 10 millimeter diameters, 157 square millimeters. Then we compute for the excess shear. This will be the required computation for that matter. And then the formula, and it happened, napakalaki nito. So gagamitin natin yung maximum na 260. So, D over D yun.
Niyo ba? Anong tanong? Walang ganun.
Ito yung beam section detail.
Yan.
Hindi ko alam. Totoo
And then we check for the bond stress, but be back in this link first. Thank you.
Recording stop.
Hello? Yes, sino sila? Sino po? Wala po. Sino po sila? Okay.
Pag ganun mahal, wrong number na ako. Huwag ka na magtanong ng kung ano. Mahirap yung kasi mamaya hinuhuli ko lang kung sino-sino. Papakiin to ng pangalan, mahal. Comment mo yung buong pangalan ko. Surname first. Hinuli yung mga biting na red light. Yun.
Recording in
These
progress.
are the allowable band stress here. For top bars in tension, the allowable band stress notated as Greek letter U sub A is equal to 7.18 square root of FC prime over the diameter of the bar in consideration. Other than top bars in tension, that will be mu sub A 10.14 square root of FC prime over D. For all compression bars, that will be mu sub A is equal to 0.54 square root of FC prime.
Ilan?
We dwell on the singly reinforced rectangular beam. So we check for bond stress.
Napakanan ako.
We consider other than top bars in tension. So this is 10.14 square root of FC prime over D. Because the main bars are placed at the lower portion of the beam, so that will be tension area. Other than top bars is compression, so that will be 10.14 square root of FC prime. This will be 1.65 as the allowable. And then we compute for the actual. So this will be the peripheral of the considered diameter or reinforcing bars by 28 times 3 because we are dealing with 3 main bars here. And then we compute for the actual bond stress, which is equal to V. That's the actual shear divided by the peripheral or the considered perimeter of this main reinforcing bars, and then the JD. And this is less than 1.65, so this is safe in bond stress. So if that will not be safe, we are going to revisit our dimension for consideration of the reinforcing bars. Fellow learners, I'd like you to take a look at the beam section detail. Since we're dealing with simply supported beam, the maximum moment is located within the midspan as positive moment that provides concave upward, meaning the tension part will be at the bottom. So the main reinforcing bars will be placed at that particular area. This will serve as mandatory bars only because we do not have requirement for compression bars. I did state the concrete cover always 40 millimeters to avoid corrosion or the effect of in the reinforcing bars. This will be 10 millimeter diameter steel wraps. So what we have previously as the distance 260 millimeter on center is this distance, no? 260 millimeter for the steel wraps. based on the result. So this will be 216 Newton. Well, in actual design, we normally present nearer near distance within the proximity of the support reactions here. So usually we set it up as 2
Kalapit
bar
na pala.
or 2 stirrups spaced at 50 millimeter diameter,
Dito na yung class A. Dito
3
na yung class A
stirrups
motor.
spaced at 100 millimeter 100 millimeter, and among others.
Class A
So
motor na
in the
dito.
same manner, what you did here will be the same
Ayun, nakadaan na ako dito.
distances that will be
Nakaraan
provided.
na, pinadaan. Oh.
So first, let us have a cap
Tapos kakaanan
to
ako.
recap what we learned in this WSD. So far, the underlying principles for the singly reinforced requires the beam coefficients or the beam constants MKJ, and the moment coefficient resistance M as the service moment or the capacity. We have RBD squared with the guiding ideal ratio AS M over FSJD, or we can compute it using the balance steel ratio BD, and as a function of the strength of concrete FCK over 2FSBD. For the doubly reinforced for tension and compression, we start with the internal couple MC1, MC2 for the compression side, and then the compression bars AS prime based on the balance moment C1 J1D. Then C2 J2D
Ah.
Yan yung...
will be AS prime FS double prime for C2, and then J2D. We have a situation for FS double prime.
Wala, di ba marami?
So, and then we compute for MP1, MP2, we compute for AS2 based on the ratio of the excess moment
Pero tingin mo, marami.
divided and the FSJ2D, and then the AS1 from the balance moment or the service moment computed, and then we add this as the steel reinforcement for the tension side. Then we design the web reinforcement, also the stirrups or the shear reinforcement. We compute for shear at D distance. We compute for the actual shear stress based on the computed actual shear. So apparently you need to have correct support reactions, correct shear diagram. Then we compute for the allowable shear stress, 0.09 square root of FC prime.
90 grams.
For for the S, A, B, and B, B prime, B. And then S max, D over 2, S min. Actually, this can be computed as S. This is A min, so this will provide maximum distance. This will provide minimum distance. You can reconsider it. And then the location wherein we're going to place the stirrups, this will be X to be computed. But this X has provided recommendation must be extended D distance from both extremities. So this will be the actual range of where we are going to place the stirrups, X plus 2D. We check for bond stress, shear over sigma sub O, JD. That sigma sub O is a perimeter of the 3 reinforcing bars. I mean, not 3, depends on the number of reinforcing bars and reinforcing bars. So this will be top bars in tension for the allowable 7.18 square root of FC prime over D, other than top bars in tension 10.14 square root of FC prime over D, and for all compression bars we have 0.54 square root of FC prime. Then we set the beam section detail. Fellow learners, the algorithm for what you're going to deal with the underlying principles of design using working stress principle. So basically, what we have here is considered location of the inflection point and consideration of placement of bars when it comes to development length. So this generally presented as this one. So we have a considered set up. Kindly go over, take a look at the figure here. So this will be the considered bars, cut bars from the excess moment that will be considered in the tension side, and this will be the continuous bar um, usually extended all throughout this column or supports here and like in this side. We also have the tension bars here at the since we are dealing with the continuous in that sense. There will be tension bars here. This will be the representation of that development length. Please take a look at this one. ACI code requirements on positive moment reinforcement must be continued uninterrupted 6 inches into the support. At least 1/3 simple beam, 1/4 continuous beam. Negative moment, 1/3 of the reinforcement.
Lapit na eh.
Must be continued uninterrupted. Halimbawa, siyam,
Ganda.
yung kailangan sa tension bars.
Ano ba yun? May
Yung uninterrupted, yung at least 1/3 na sinasabi. Must be continued. Okay? So,
Bagal.
kinwalify niya yung representation ng development length dito with the corresponding embedment length. Kindly go over with this presentation. I leave that to you. And you go over with the corresponding overlapping for the development length and the considered magnitude here pertains to the D effective depth and diameter of bar and the clear span LN here. Please go over with this two figure that represents the cut-off points or the consideration of the development length, not the cut-off points here.
Yung ulit malapit na tayo.
And then for nearly
9 minutes.
the span, equal spans for 50% of steel is cut. Ito yung sinasabi naman natin.
Doon sa dati.
For the tension side, for the compression side, it requires doubly reinforced.
Dati yung...
But since we are dealing with continuous beam here, so we are considering negative moment and positive moment. So essentially this has been anchored from the previous slide, but in here has been simplified as 1/3 if you are dealing with interior support and 1/4 if you are dealing with exterior support. Just be mindful that this one must be considered. There must be considered embedment length here and bend length
24 lang po.
there. Please revisit the bend length. Bend of the considered main bar at the top. So that will be about 12 D and 40 dB for that matter. You kindly recall what we have discussed previously for those beam section details. You can utilize this one instead of cutting it as crank bars, continuously presented, bent up. So in the same manner with this one. And then we have, well, the splice code specs. Kindly go over with what we have discussed. 40 dB, 40 times bar diameter as a minimum, or up to about 60 dB or 100 dB. So please go back with that as a splice length. So that's the recommendation of our code. And for nearly equal spans, for less than 50% of steel is cut. So hindi lahat ini-splice. No? Okay. Please go over with this one. I leave that to you. Revisit this one. Some of these are merely recommendation, but they often use this one. L/8 L over 7, or others L over 5. But we can utilize L over 5 or L over 7 as governing recommendation in our design. It's up to you as a designing engineer there. And then the standard bend and cutoff points, approximate bend and cutoff points can be used in continuous beams or one-way slabs where the following conditions are satisfied. Not more than half the reinforcement is bent or cut off. And then 2 or more spans. Unit live load does not exceed 3 times unit dead load. Loads are uniformly distributed. So, ang sinasabi lang naman dito, basta huwag kang magtaas ng ano. Yun, nalapas sa kalahati. May continuous, may nakadiretso pa rin on both sides.
Paano ba to?
Ito kasi hindi na masyadong tinitingnan yung sa live load, pero ang mahalaga kung uniformly distributed, well, call na ng designer yan kung gusto niya naka-bent up. Kasi pag binent up mo nga naman, na somehow nako-compromise yung distance na L over 3 or L over 4 if you are dealing with interior or exterior support. Nevertheless, you can add additional reinforcement there. Kaya tayo somehow merong mga stiffener na sumusuporta doon sa mga ganong tipo ng setup. Pero hindi natin sinasabi na kasama yon. This has been included in the design of the main reinforcing force. Spans are approximately equal to width. The larger of two adjacent spans, not greater than, shorter by more than 20%. Unawain natin, no? So, yung by more than 20%. So, kung halimbawa, may dalawang span, L1, L2, so, tingnan mo lang yung difference nila. Pag ano niya ay sobra na sa 20%, di mo pwedeng gawin. Okay? So, tingin na lang dito sa figure. And then, we consider this one as well.
Ayan, malapit na tayo eh.
Okay?
Diretso na.
So, please take note of the splice recommended requirement, splice length. The area wherein you're going to set your splicing, yung pagdudugtong, hindi dinudugtong basta-basta yan. May mga corresponding areas yan. Highly dependent on the situation of the internal effect of the induced loading. I'd like you to be adept with these figures here. Let's set up ourselves for the articulation number 4. For the beam loaded as shown, designed completely for positive and negative maximum, use the strengths 20.7 megapascal, 138 megapascal. For concrete and steel respectively, dimensions 275, 550, live load 40. We start with the given. So I believe you're familiar with this. So we start with it, 650, and we compute for the dead load. We compute for the service load. We add apparently this one to the service load. So we say 44 kilonewtons. Then we solve for the support reactions. I believe you know this already by using your propensity in engineering mechanics. RA and RB. Then we draw the shear diagram. This will be anchored from what you learned in your strength of deformable bodies and structural analysis or theory of structures. So the point of zero shear is equal to this one by similar triangle. Then we draw the moment diagram. This is the moment diagram. By virtue of what we learned in computing the location of the point of inflection or the point where the concavity changes, so we are going to set a moment equations there and the loading, and then we compute for it. We set that into zero because we are after for the intended purpose of computing the point of zero moment. And this is equal to 6.8875 meters. Okay, so we first design the dimensions. So we start with the modular ratio ES over EC, the beam constant K, NFC over NFC plus FS,
Kaya nga, di ba?
J1 minus K over 3, the moment coefficient resistance R,
Nilagpas
we
ako.
consider the negative moment first. So with the RBD squared as M, we compute for the actual D here. And this is less than the supplied D as 550. So we will
Yeah.
design it singly reinforced.
Dito na ba?
We compute for AS. It turned out that this requires two 25mm main bar.
Siguro.
This will be the beam section for the negative moment. So that will be placed at the upper part. It just so happened that this have the same comparable number for mandatory
Ayan,
first.
siguro.
So this 615 is the added value of the D prime for the effective depth, supplied effective.
Ano naman?
Then we consider the positive moment.
Gusto bumalik
We
pa ako
compute
kasi-
the same manner, the D, the supplied, we compared for the supplied D, and this is greater than this one, so we are going to design it
Mahal.
as doubly reinforced. We start with balance moment, 1/2 FCKDB J1D or C1 J1D,
Ay, tinakaran nilusutan natin.
and this is the balance moment, and then the AS1,
Ay, yung dulo na yun. Nandiyan tayo.
this will be AS1,
Laki yun.
and then the AS2, then we set the D prime at 60 here, and then we compute for the total AS, and I utilize 25mm diameter. It requires 8. The requirement for FS double prime, so we need to compute first for the actual compressive stress, which is equal to 6.63. We compare the 2 and FCS prime with the allowable stress. Well, it turned out this is less than. So we will utilize this formula 2n minus 1 FCS prime.
Dito sila sa gate.
And then this is equal to 112.65. If this is greater than the difference of the allowable and the FCS prime will be used. Then we compute for the compression bar requirement. And this will be the excess moment divided by FS double prime
Madilim.
times J2D, which is equal to effective depth minus D prime.
Ito.
It requires 5, so we have this. And this is the correct setup already. We did present this in our previous discussion.
Oh, memorize.
We are about to consider this for checking the shear, the distance. So by virtue of what we have computed for RA and the uniformly distributed and the effective depth, this will be the actual shear. This will be the actual shear stress. This is the allowable, then we compare it. Well, obviously less than the actual, so we provide shear kasi maliit ito. Ito malaki, okay lang. Pero usually nilalagyan talaga na even if the allowable is greater than the actual shear, we still provide stirrups there, so as a minimum requirement. This is the considered area to be utilized as stirrups, and this too, I have explained this already.
Kanan.
This is the excess shear,
Tulay.
and this is the distance of the stirrups. We compare it the two parameters, 275
Di ba
and
kaliwa?
380.80. So we will utilize the lowest in value, and this is 182.32 among these three. Say we use 180 millimeter on center.
Kaliwa ba?
Kaliwa, mahal. Ito yung pinasa.
And the place or the setup wherein we're going to place the stirrups will be based on the similar triangle. So this is equal to 2.8937 meters. So as indicated in our shear diagram, well, you can do that.
Bakit may ganito?
This will be V prime V. So in essence, we can compute for X of 1, which is equal to 1.48 meters. So I did say that by code specification or recommendation,
Kanan.
we need to extend the region where web reinforcement is required by D distance, both sides of X. So this will be 2.58 meter now, which verify this shearing requirements at intermediate point. So that will be half of the X plus 2D. And then we look for the shear at that intermediate point. And this is RA minus W1. Well, you can go back to the actual beam.
Bush.
RA shear minus W times 1.20. Then we compute for the actual shear for the intermediate point. And this is greater than the allowable 0.41 computed a while ago. So we provide shear. So based on the formula AB, FB, V prime, we did get the difference of this was excess shear. And we did compute this one. This is given, this is computed, this is given as well. And it requires 358.12 millimeter
Okay.
distance.
Punta na dito.
For D over 2, that's 275. For AB over 0.0015B, 380.80. So we will utilize the list of these three values. So that will be 275 on center. And then
Maniobra ko na.
we check the shear at B left of the of the support reaction. So that will be the considered. Well, you consider this one as from the left of the second support, and that will be 141.075. This is the reaction, the uniformly distributed, the effective distance. We compute for the actual shear on that side, and this is greater than the allowable computed a while ago. It needs shear reinforcement or web reinforcement for stirrups. So we do the same computation. It turned out we have 151.51 millimeter. We compare that to those allowables here. So we choose the least value, which is 151.51, say 150. We adapt this. So far we have 180, 275, and 150. Then we set the location wherein we are going to place this one for the next set of spacing. And on the other side, we have this as 2.9 for the extension of the distance. So we check at the intermediate point, we compute at the intermediate point for the actual shear of that, actual shear stress for that matter, and we compute for the distance as well. And we adopt 275. Because of the comparison of 275 and 380 and 303, the least value here is 275 millimeter on center. And then we check shear at B right, at the free end. So 66 minus 44.55. Then we have the actual shear, and this is less than already. So since this is less than already, it does not directly imply that we will not place any stirrups at all. We need to check further for the magnitude of this one, whether this is greater than 0.41 or half of the allowable. So within 2D distance, provide shear reinforcement, 3/4 of the effective depth, or 300 millimeter, whichever is smaller. So if this will not fall within this recommendation, we need to set up, say for example, at least stirrups for that matter, say every 300 millimeter on center or every 400 millimeter on center. As much as possible, we need to provide stirrups.
Hindi, may tubig naman yung magkasa ko na kasi.
And then we adopt 300 here based on the comparison of the three values and this one, no, the other values. So we adopt the 300 here on center.
Alcohol lang yung gamay niya.
We check for band stress. 2 points to consider for band stress. At supports where shear is maximum.
Diyan na sila.
At point of inflection where moment is
Ay,
zero.
nagbubukas ng pinto.
So at support, we have this one.
Ikaw ba yun?
Viper yun.
Other than tension, tampers in tension. And then we compute for the considered shear there, so that we will know what will be the required consideration for the band stress. So we do the reverse.
Oh, 8 na.
So So
Saan na kaya ako
we
dumaan sa
compute
UP?
for sigma sub O based on the
Malayo.
formula V
Kain muna
over
ako.
the
Kumain ka muna.
um,
Eh, kaso pa, bigla silang dumating.
Hindi,
allowable
hindi na sila nakita ko.
Tatakbuhan.
bond stress and
Oo,
the
kanina.
JD.
Maraming paa.
And then for the number
Ano
of
sa rear view? Dahil paa.
required bond stress
Oo nga, nandayang pa.
for the reinforcement for bond stress. So this will be 2.8 in say 3, 25 mm. Eh, 8 naman yon, so okay lang. Nasa baba. So at B, so this will be the reaction. So top bars in tension, di ba negative moment yun? Top bars in tension. So we have this as this one. For the same computation, so we have 263.13 for the perimeter. And this will be utilized to compute the number of bars to be considered in band. So 3.35 say 4, eh dalawa yung nakalagay na main bars, so kulang. Dagdag tayo ng dalawa para sa band requirements. So yung dalawa na yon, aside from the two main bars, we're going to place there na may cut-off length. Usually yung L over 3, naalala nyo doon sa cut-off length in previous slides, L over 3 plus embedment length plus depth o yung squala. So yun yung ginadagdagan natin para sa band dahil kulang ng band para
Hi,
doon.
guys.
Sa inflection point, kung saan zero ang moment, so ito naman yung shear
Hello
natin.
po.
Then we compute for this one, so upwards in tension.
Apo ka agad sa bubong.
And then yung sigma, same value, same process to do compute the value of the perimeter and the number of
Yes,
tables.
pa yung pinakalikod.
So dito kailangan ng 4. So kasi wala naman doon tayong requirement sa point of zero moment, wala namang main bars doon eh. So na-compute dito 4. So meron siyang requirement na 4. So ilagay natin, i-consider natin dito, no? Sa A, 0 naman yung AS doon. Sa band, kailangan ng 3. Sa flexure, wala rin, 0 rin.
Sa bubong.
Sa positive moment, dun sa mid-span ng AB, so 5 yung compression at 8 yung flexion. Wala namang kailangan na sa band kasi sufficient na yung 1.
Haba ni kayo, hindi siya kasha.
Sa point of inflection, wala naman talagang compression at tension bar doon, kailangan ng 4. Sa B, kailangan ng 2 doon, 2. Meron ng 2 doon, di ba? Eh, pero kailangan din ng 4. So, dadagdagan din.
Uy, asan na yung chinelas?
So, ito yung siniset up natin doon sa about mid-span. And this will be the setup at the supports within
Oo
B.
nga po, may
Diba?
exam po
Na
kasi
alala
kami
nyo
eh.
sa previous slide. Right there.
Kami nang bukas pa kasi labahan namin.
Okay lang po.
Ay, sabi niya, dadali na lang daw.
Don't get overwhelmed with this figure. Isa-isayin natin mga utol. Okay? Sa section na to, iba, meron tayong, hindi yan dito.
Lowered tayo ah.
Dito sa gitna. Kasi kailangan ng 3 rito eh, kung maaalala. Ayun o, 3.
So, paano palabas?
So actually, 3 lang yon, may extended na 2 rito, kaya naging 5 yan. Pero pwede rin naman 3 yan. 3 lang naman ang required. Tapos yun sa, ito okay naman dito daw. And then dito, kailangan ng 4. So nilalagyan lang ng extended na 4. Kaya kung magpapansin nyo, naka-terminate lang naman dito yan.
Ito pa rin yan, lowered.
Pwede rin naman i-extend yan.
May slip lang.
Kaso 2 lang ang kailangan dun eh. 2 lang.
Hindi ko naabutan.
Kaya yung nilagay ko na lang yung
Easy kayo kayo
Kinamit ko na lang dito para
Nabot
tipid
naman ni kayo ito?
yung 1.5
Oo,
na
asawa
yung
pa
bagay
rin
din
naman
yun.
yun.
Pag pumutol ka ng
Tinulagkat
isang buong
natin yun eh.
6 meter, ang presyo
Ano
ngayon
kayo?
kulang-kulang 500, magastos na kagad eh. Kaya
Bakit?
napakahalaga
Bakit makain?
ng cutting list
Pag
para
nakain,
minimize
Makain.
ang
asad
wastage.
kanta na lang.
Oh my God.
Yan yung mga bakal.
Tapos siya,
Ito,
ano ba?
mga utol, yung
Bakit?
posisyon ng bar na to
Charot.
ay yung 5 rito,
Paano palabas, boss? Kaliwa
Walo
na.
rito. Kung maaalala nyo, may walo tayo.
Saan pa pwede?
Eight,
So,
seven.
Ma'am?
apat itong diretso na to, saka
Susunod na
apat
lang.
ito.
Oo.
Kung sinabi niyang apat. Kung hindi, wala naman nakalagay dito. 212 25mm diameter meter. Yun yung nakadiretso lang. No? Na nakalagay. Yung 6. Ikaw na bahala mag-placing. No? Pero, kinocompute
Hanggang
niya
saan bahali
which
to,
you're
boss?
going to do after
Malalim.
this discussion. So, if you will notice L over 5,
Diretso ako, kanan.
and for the purpose of instruction, if you will recall the computation of the
Hindi subdivision.
intermediate point for the first intermediate point, we have 1.29 and 1.20.
Ah, pwede
For
rin.
the second is 1.45 and 1.1.
Sundan ko na lang itong ano.
Sige, isa-isain natin. Yung 180 kanina, naalala nyo? 180, ito yun. Mula sa intermediate point na yon dito. Yung 1.29. So, mula rito, hanggang dun. So, usually, this will be spaced at 180 accordingly based on what we have computed. But the designer opted to consider 3 at 50 or 2 at 50, 2 at 100, 3 at 150, rest at 150. So, ganun yung ginagawa. So, kung 8 yan, didiskartehan mo na basta may 180 dito.
Bakit?
Tapos,
Asa mama?
masinsin na rito.
Ah, sinamahan doon.
Ganun yan. Yung for the second intermediate point na 1.29, naalala ninyo, 275 yun ang compute natin doon.
Ka-eshi
So
lang.
kung i-divide mo to sa spacing na 1.29 sa 275,
Lahat kayo
so mga ganito, 3,
Pansinigol?
4, 5, mga 5. So, well, maglagay ka ng stirrups doon. Ang distansya ay 275 millimeter. Mula rito, dito magsisimulang
Hindi,
masinsin.
mamaya na lang.
275.
Tagal pa naman eh.
Oo nga.
Tapos doon sa left side,
Ay, sino
left
nagsawa sa
side,
inyo?
unang intermediate point. Naalala nyo,
Mainit dyan din.
yung space natin, 150. So
Paano
mula
tubig
rito
na
yun,
sa
sa
inyo?
1.45,
Maraming putik. Ah, hindi naman.
heading towards this
Ganun
one.
ang lalim,
Dahil
ano ba yun?
pwede naman puro 150 yan, pero the structural designer opted to
Pati sa
consider
bahay nyo. mama.
nearer distance at the proximity of the
Sa may gate,
supports.
no? Yung
Mahalaga
pagkakita
kasi
namin.
yun. So dito nagkakaroon ng
Wala pa
problema
pwedeng daanan
pa.
dito.
So kaya sinisinsinan natin.
Balikan, ay, hindi
So
ko.
nilalagay usually at 50 millimeter, 2 at 100 millimeter, 3 at 2 at 150, rest at 150 kasi 150 naman. O kaya 350 millimeter, ganun lang. Pagkakasya mo, di ba? Sa hindi ka kukulangin dito na 150 ang pinakamalayo mo na distansya ng spacing ng stirrups dito. And then for the second intermediate, alala niya na 275 yon
Pwede ako maliwa dyan.
on center. So mag-start lang dito, 1.45 divided by 275. Pwede mong i-maintain yung 275 dito. Yan, ito 275, yan 275. Pwede mong sinsinan dito. No? Basta pasinsin papunta doon sa proximity of the support. And then dito, wala namang nakalagay dito. Usually, the designer opted to place
Parang ba tapos?
10 millimeter diameter stirrups spaced at 200, no? 200 millimeter on center o kaya 300 millimeter on center. Ikaw na bahala doon. Wala namang sinabi ko ano. So as a designer, lagyan lang natin ang stirrups para makadagdag siya to mitigate the risk of counteracting the lateral forces or the tension stresses created by lateral forces or yung earthquake or seismic forces.
Natas ka na.
Then alala nyo sa kanan, 300 mm yun na compute. Ito yun. So 300. So kung di-divide mo lang sa 1.5 yun, so mga 5. So ang ginawa niya, sinsinan niya na lang dito. Pwede naman. Tapos yan. Dagan mo na lang kung gusto.
Hindi pa.
Basta may malagay ka rito na 300. So yan yung 6 nakalagay dyan.
Kanan
Fellow
kaliwa
learners,
ako.
ito yung setup
Pa-edge
ng
yan.
pagde-design ng main bars, shear reinforcement, corresponding distances of spacing of the stirrups, and the location wherein you're going to place the stirrups there. So may natitira dito, no? Usually, wala naman dapat ilagay, pero sinabi ko nga na nilalagyan din natin. So, this is the WSD principle. Please be back in this link. Thank you.
Recording stop.
Yan, napapalagay na yun ang pangalan. Gilid mo na kaya ako.
Hanap ka na ng ano. Right lang.
Teka lang.
I see!
Mamaya, doon na lang sa ano.
Okay. Hala, butas!
Olin.
Shirt ko.
Pagka malapit na lang. Tagal naman na siya pumasok. Baka mo.
Okay.
Papalagay yan ang pangalan.
Ay, lagay mo na ano.
Traffic sa EDSA. Pag tayo dumaan sa ano eh, Q-Up eh. Ayan na. Lagay nyo.
Recording in progress.
Ano may pangalan ko? Lagay mo na.
On video, everyone,
Ang video to.
kindly key in your name. Please, on your video, I'm going to take a peek in a while.
Ayun na, Daryl. Pinag mo na lang, Daryl. Sunod-sunod na yan, Ranji. Okay na yan. Tapos close mo yung video. Tapat mo sa akin.
Turn right onto Epifanio de Los Santos Avenue, Pan-Philippine Highway.
Ayan.
Okay, kindly on your video, peek lang, magkaroon lang tayo screenshot.
Pero sabi ko okay na ako. Stop mo na ako yung video.
Okay, may clarification ba?
Okay na yun.
Or question or concern? Sa design, sa pagde-design natin, well, napakahalaga na naka-set up yan, na nagsisilbing blueprint natin para mailagay sa actual. Napakahalaga rin ng paglalagay sa actual kasi hindi ganyang kadali ilagay sa actual yan. Lalo na pag napakaraming bakal, napakasinsin ng anilyo, diskarte ang kailangan ng mga magagaling nating kaibigan
Ano naman yan, di ba?
sa construction site. Kasi hindi basta natutupi yan. Eh kung 28mm diameter yan, hindi mo basta matutupi yan. Kaya yung diskarte bago ilagay doon. Lalo na pag suspended yan, nasa second floor ka na, third floor, fourth floor, tapos sa mga dinadalang bakal,
Ano sanabi niyo?
28mm diameter, 25mm.
Babalik lang ako doon.
Kahit na 16mm diameter, which is the minimum meters, mahirap pa rin pag marami
Ano?
na isusuksok mo sa biga. Kaya dinidiskarte yan. Okay. Bago maglagay ng sidings ng biga o yung forma sa biga. Kasi pag nalagyan na ng siding siya, mahirap din ilagay lahat.
Naka-U-turn ata yan.
Kaya, well, ang ginagawa na ako, based on my experience, kanya-kanya na mag-discarte yan. Yung
Oo.
bakal muna,
Pwede ba?
para na freely nakaka-move yung mga
Dito?
kaibigan na,
Pero hindi na sa picture mo lalabas ah.
na mga magbabakal.
Hindi ba sa yung ano lang doon?
Ang lalaki ng mga muscle.
Yun eh.
Teka lang.
Pag nag-bend sila, 16mm. Wala kasi akong 20mm sa actual eh.
Patay mo na yung ano.
And then, yun lang, yung kinukonsider namin na anilyo, 10mm.
Examine na.
Pwede.
And then,
100 meters, turn left.
yun lang. Pag medyo marami yung kailangan bakal, nakaka-move sila kasi wala pang wala pang sidings, forma. Formworks. Sinabi ko lang. May tanong ba?
Si Kai.
Nabigyan ako ng oportunidad when I was at your
Kaya na-miss ko rin
mula
kamay
first
mo.
year pa lang ako. Hindi naman ako nagkaroon ng ganong tipo ng sitwasyon na medyo nakapag-aral sa ganito. Gusto ko makapag-aral before sa institusyon natin ngayon.
Kay Princess eh.
Pero hindi ko wala kaming sapat na paaral dito.
Ay,
Kaya produkto ako ng State University.
Lamig.
So, kulang ang pambaon, kulang ang mga pambili ng project. Dahil CE ako, nag-pion ako. Kaya ang kulay ko, ganito. And then, kasi para ma-identify ko na rin, ano ba yung anilyo, ano ba yung
Gusto
ganito.
mo i-waste mo ano ba yung timbahan?
Sinasabi ni Sir, hindi ko naman
Ang pangalan?
maintindihan. Pero hindi ko sinasabing mag-pion kayo.
Malapit
Hindi
sila,
sinasabing magbakal kayo. Actually, ginawa ko stillman.
Dumi na
Ang sinasabi ko lang,
Domingo.
you have that opportunity to see it in the internet. Andiyan na lang eh. Pwede mo nang tingnan lang. So, gawan nyo na lang. Kindly provide time for that. Mahalaga yan para sa atin bilang designing engineer. May iba pa bang tanong? Mukhang wala na yata.
Wala naman po sir.
Ay,
Oy, salamat. Sige, thank you. Bago tayo mag-iwalay, share ko sa inyo yung senior din sa akin. Kaya lang ibang
Hello,
author.
sir.
The premise of Atomic Habits by James Clear is that it's very easy to underestimate the value of making small improvements on a daily basis. Too often, we convince ourselves that massive success requires massive action. If you can get 1% better each day over the next year, you'll be 37 times better by the time you're done. This applies to all goals, whether it is losing weight,
Ito ba?
winning a race, or starting a business.
dinaan
Small
ako.
habits can compound over time. In fact, according to Atomic Habits, habits are the compound interest of self-improvement.
Siguro kanina
The
pa
same way
Wala natin nakakasahan ako doon
that
sa ikot
money multiplies through compound interest.
Ikot ng...
The effect of your habits multiplies as you repeat them. They seem to make little or even no difference at all at the instant, but on any given day, the impact will be delivered over the months and years, and that will be enormous. You probably already worked it out, o alam mo na ito.
Sino mo nga dyan?
Itong atomic habits are small, tiny habits, just like atoms. These are small, but these have the ability to be mighty. Atomic habits become mighty when these are repeated hundreds or even thousands of times. Pero alam niyo ba, bad habits ay nagko-compound din. Putting off a project for tomorrow seems to make no difference. But when you repeat this type of 1% error day after day, these tiny errors can compound into toxic results. Success is the product of daily habits, not once in a lifetime transformations. But be aware that your outcomes will lag behind your habits. For example, eventual wealth is lagging measure of your saving habits because of the lag factor. You should be far more concerned with your current trajectory than with your current results.
Pwede mo na
Remember
yung
yung pinag-usapan natin sa bow and arrow, the hallmark of any compound process is that the most powerful outcomes are delayed. Habits appear to make no difference until we cross a threshold and unlock a new level of performance. This is one of the reasons why it's hard to build habits. You make a change, fail to see a tangible result, and decide to give up. Habits need to persist long enough to break through the plateau of latent potential na sinabi natin before. This takes time. If you're complaining about progress early on, just remember your effort hasn't been wasted. It's being stored up. It's just that you haven't broken through the plateau yet. When suddenly
Paano gagawin?
Kaliwa ka.
you do the truth, people will think you're an overnight success. If you highly regard atomic habits, you essentially forget about goals. You concentrate more on systems.
Tama
Goals
naman
are
na.
about the results you want to achieve. Systems are about the processes that lead to those results. Atomic Habits states that if you focus on the
Ayun yung
system,
gagawin mo.
the goal will take care of itself. There are a number of reasons why you should focus on the system. One of this is because winners and losers have the same goals.
Liwag ko sa cellphone
Second,
ko,
achieving a goal is
Okay.
only a momentary change.
Saan na tayo?
Goals restrict your happiness. Goals
Tay,
are
galing kanina
odds with long-term
May
progress.
7-Eleven dito sa kami.
If you're having trouble changing your
Ano yun?
habits, the
Surprise.
problem is not you. The problem is your system. focusing on the overall system rather than a single goal is one of the core themes of Atomic Habits. You do not rise to the level of your goals. You fall to the level of your system. Atomic Habits are small habits that can have a huge impact
Hindi, diretso
if
mo na yun.
performed over months or years. The goal isn't to make a single 1%
Baka mas mura
improvement,
to, baka
but to
padaan
make
eh.
thousands
Hindi mo katamaan
of
doon. Pag U-turn
improvements.
mo,
It's not
dire-diretso
of
mo
atomic habits
may
stacking
drive
up.
to sa SB.
It's one part of a system that meaningless even if you logically know these are the right thing to do. Gradually, as you continue to stack small stages on top of one another, the scales start to tip in your favor. Eventually, if you stick with it, you hit a tipping point, and suddenly it's easier to stick with good habits, and the overall system is working for you. Merong isang piyon na inutusan, helper, construction worker, inutusan na patibag yung konkreto na pader, concrete wall. Tipagin mo yan, kinuha niya yung ball hammer, yung maso, and then he started hitting it. He initially hit it once, twice, pangatlo, pang-apat, until such time it reaches 100 blow of the ball hammer, bumagsak yung concrete wall. Napabagsak ba nung piyon o nung construction worker yung concrete wall because of his first hit? No, it's not. Napabagsak ba niya noong second hit? No, it's not. Napabagsak ba niya yung concrete wall sa kanyang 100 hit? No, it's not. Napabagsak niya yung concrete wall because of the continuous pounding on the wall, just like atomic habits. Mga utol, at this point, maraming salamat sa kabila ng ating schedule. Pinuntahan niyo ako, ginawa niyong ganap na may kausap ako
Ayan na
dito.
naman.
Be blessed, everyone.
Yes po,
Be
sir.
humble. Be safe.
Kapit kayo.
Sana kami, sir, hindi rin bumagsak.
May motor.
Thank you, sir.
Thank you,
God bless
sir.
po.
Thank you, sir.
Thank you, God bless po. God bless you po. Thank you po, sir.
Habol mo pa eh, loko.
Be blessed, sir.
Dari lang na. Tignan naman eh.
Recording stop.
Signal, di ba? Ito ang computer. Hindi? Pwede.
Babay lisensya. At dali mga pulis! Sibol na naman sa taas.
Green ba? Green
Oo.
na.
Hindi naman sila lahat.
Mas manamahal yung ano. Yung recording. Ay, ano?
Oo, hindi ko